Imagine the absolute peak of high school math challenges, right? The International Mathematical Olympiad, the IMO. This isn't your standard math test. We're talking problems that demand, like deep human insight, real creativity, and seriously rigorous proofs. And for years, it's been this kind of Everest for AI, a benchmark where even the top large language models, LLMs, have really stumbled. But then something genuinely groundbreaking. We're diving into new research today showing Google's Gemini 2.5 Pro. Using this, very specific strategic pipeline, it actually solved 5 out of 6 problems from the completely new, unseen IMO 2025 competition. 5 out of 6. That's not just good. That's like human gold medal territory.
Yeah, and this is way more than just spitting out the right number. It's a real showcase of genuine reasoning in these models. And the key thing, they use problems released just days before testing. That means 0 chance of data contamination. It proved the model can actually generalize, think creatively on stuff it's never ever seen before.
Absolutely. So in this deep dive, we're going to unpack exactly how they pulled this off. We'll look at that innovative self-verification pipeline that was so crucial, and maybe most importantly, what this huge step means for AI tackling complex problems in the future. Get ready for some serious aha moments, I think. Let's unpack this a bit more. What exactly is the International Mathematical Olympiad, and why is it such a notoriously hard challenge for AI? So for anyone not familiar, the IMO, it's the top annual competition for the best pre-university math students globally. Started back in '59 in Romania, a tiny group of countries. Now, over 100 nations take part. The format is intense. 2 days, 2 4.5-hour sessions, 3 problems each session, graded out of 7 points each. But the crucial thing, what makes IMO, is the kind of problem. They require real insight, original thinking, pulling together different math concepts. It's about creative proof-based reasoning. It's about, thinking, not just calculating.
Right, and that's what makes it such a fascinating test for LLMs. These IMO problems really push their ability to do complex, multi-step logical deduction. It's not just pattern matching or pulling facts from memory. If you look at other benchmarks, things like GSM-8K or math, LLMs do pretty well there. But often that's because those problems are more about recognizing patterns or, frankly, regurgitating stuff similar to their training data. High school level math, mostly. IMO problems, though, they're a whole different level. They shine a spotlight on the limits of current LLMs. Things like difficulty generalizing, the tendency to hallucinate, making stuff up or relying on sort of superficial tricks. The IMO really asks, can these models truly reason like a mathematician, build solid arguments from scratch? Or are they just fancy parrots repeating solutions they've kind of seen before? It gets to the core of their reliability for like science or formal verification.
Yeah, and we've seen progress, definitely. Things like chain of thought prompting, SOTT, where the model explains its steps. That helped. But even with SOTT, the best models have really struggled with Olympiad level stuff. They often make logical leaps or their proofs just aren't solid. This paper is claiming they've bridged that gap, which is a really big claim.
It is, and it brings up that super important point you touched on earlier, evaluation. How do you test fairly when the model might have seen similar problems or even parts of the test data during training? Data contamination is a huge issue, especially when you're trying to measure reasoning, not just recall. So the researchers here were smart. They used the just-released IMO 2025 problems, like days old. That ensures it's a clean test, a genuine measure of problem-solving on unseen challenges.
That makes sense.
And it's worth noting, this is a hot area. OpenAI, Google DeepMind, they've also recently announced similar gold medal level results on IMO 2025. It's clearly a major focus right now.
Okay, so the how. This is where it gets really interesting, isn't it? How did Gemini 2.5 Pro actually manage this? It wasn't just feeding it the problem. You mentioned this self-verification pipeline. Sounds complex. What does that actually involve? It's like a 6-step thing.
Exactly, 6 steps. It's quite a sophisticated process. It starts, logically enough, with step 1, initial solution generation. They prompt the model to generate a solution, often multiple times to get different starting points, different approaches, and the prompt itself stresses rigor, getting the proof right, not just the answer. But interestingly, and this matches what others have found, the initial quality, often pretty low, lots of errors or gaps. So this first step is really about exploration, casting a wide net. Then, step 2, self-improvement. Now, Gemini 2.5 Pro is powerful, but like any LLM, it has limits on how much it can think at once, its context window or token budget. about 32K tokens here. That's often not enough for a complex IMO proof. So step 2 basically gives it another go, another budget to review its own initial work and keep thinking, refine the argument. And they saw real improvements here. It's like letting it take a breath and continue the thought process.
Okay, so it tries, then it refines itself, but then you need to check if the refinement actually worked, right? What's this verifier part?
The verifier. This is absolutely key. That's step 3. The verifier goes through the improved solution, line by line, meticulously checking for issues, and it classifies them strictly. Critical errors, like major logical flaws, factual mistakes, 2 + 2 = 5 kind of things, or justification gaps where the argument isn't complete, maybe a step is missing or isn't rigorously explained. It might be heading in the right direction, but the proof isn't watertight.
I see. So big mistakes versus underdeveloped arguments.
Pretty much. A big justification gap could still kill the proof, mind you. So the verifier produces this bug report detailing all the issues. That's step 3. Then step 4 is interesting. They review the bug report itself. Because the verifier isn't perfect either. It can make mistakes. So this step catches errors in the verification, making the feedback more reliable.
Quality control on the quality control.
Exactly. Then step 5, correction. The original model uses that verified bug report to try and fix its solution. And this whole loop, verify, review the report, correct, can happen multiple times. Iterate, until the solution holds up or they decide it's just not getting there. Think of it like a super patient peer review process, but all done internally by the AI system.
Wow. And getting it finally accepted wasn't easy either, was it? They had a really high bar.
Oh, absolutely. Step 6, final acceptance, is tough. For a solution to pass, the verifier has to give it the green light 5 consecutive times without finding any issues, not even subtle ones.
5 times.
5 times. It makes the system incredibly robust against the verifier occasionally missing something. If it misses an error once, it's highly likely to catch it on one of the next 4 passes. Plus, the model is encouraged to carefully review the bug report each time to make sure it understands the feedback correctly before revising. It's a very demanding self-correction standard.
And just to underline the conditions, low temperature setting, meaning less randomness, more logical output. Max token budget. And crucially, no outside help, right? No web search, no running code.
Correct. Purely the LLM's reasoning power within this structured pipeline. That's what makes the results so significant.
Okay, let's get into the weeds then. What problems did it actually solve? The paper breaks it down by type combinatorics, geometry, number theory. It's quite a spread.
It is. So, problem 1, that was combinatorics, about something called sunny lines. For this one, the model got a small hint. Try induction. Now, you might ask, is that fair? Is it cheating?
Yeah, I was wondering that.
Well, the paper argues it's not really about giving away the answer. It's more about saving compute time. Induction is a super standard general technique. A human mathematician would almost certainly consider it anyway, so it's like guiding it down a very common path early on.
Okay.
And the result? Gemini rigorously proved that the number of possible sunny lines, k, could only be 0, 1, or 3. It showed exactly why 2 or anything 4 or higher is impossible for any n. That's a deep proof.
Right. And then problem 2, that was geometry. Circles, orthocenters. Sounds complex. You got a hint there too, didn't it? Try analytic geometry.
Yep, same reasoning applies. Analytic geometry using coordinates is another very general tool, especially for complex high school geometry. This one was apparently the easiest for the AI. Involved more straightforward calculations according to the paper, and the verifier was good at catching small calculation slips early on. It kind of highlights how LLMs are getting better at performing accurate calculations when embedded within a reasoning task, provided the structure is there.
Okay, then problem 3, the bonds of functions one. Number theory. That sounds quirky.
It's really fascinating. For this one, the pipeline had to generate 20 initial solution attempts. And they found that this, followed by iterative improvement, worked better than just generating even more initial solutions. Shows the power of that refinement loop.
Interesting.
And the math insights were pretty cool. It proved F1 must be 1, found relationships like Fn is congruent to n modulo p, and deduced that the set of prime factors for these bonds of functions is super restricted. It's either empty, just the prime 2, or all primes. That kind of structural insight is powerful, and maybe the coolest bit, finding the smallest constant c, where Fn is always less than or equal to c times n. That constant is 4, and it happens when n is a power of 2, like F4, 4 = 4. Nailing down constants like that often takes real mathematical creativity.
Wow. Okay, problem 4 was about sequences involving divisors. Sounds like more number theory.
Yeah, sequences based on proper divisors. Again,
Yeah.
the model derives some really strong constraints, key lemmas. Like every single term in these sequences has to be even, and every term has to be divisible by 3. And maybe the most surprising one, no term can be divisible by 5.
Why?
Exactly. These kinds of constraints pop out from the deep logic, and using these constraints, the model could classify every possible starting number, showing whether it stays fixed or eventually converges to a fixed point. It basically mapped the whole system's behavior.
Amazing. And the last one it solved, problem 5, the In-neco-ladi game. Sounds like game theory.
Yep, a game between Alice and Baza. The rules depend on this number, lambda. The model figured out the winning strategies based on lambda. If lambda is bigger than root 2 over 2, Alice wins. And it even identified how she wins using the Cauchy-Schwarz inequality.
Oh, okay.
If lambda is smaller than root 2 over 2, Baza wins. And the really neat part, if lambda is exactly root 2 over 2, it's a draw. Neither player can force a win. The game could go on forever. Analyzing that knife edge case is impressive.
So that's 5 problems nailed, but they did mention problem 6, right? A grid tiling problem. That one didn't quite work out.
That's right. For problem 6, the paper says the model only came up with a trivial upper bound, nothing substantial. It was a good reminder, As impressive as this is, there are still frontiers. Problems needing really novel insights, maybe entirely new proof techniques. Those are still hard. Human intuition and groundbreaking creativity still have a big role.
Okay, stepping back then. What's the big picture here? What does it mean that an AI can effectively match a human gold medalist at the IMO? What's the takeaway for you listening out there? Maybe you're an AI researcher, an ML engineer, or just, following this space.
Well, I think it's a truly significant step towards genuine AI reasoning. We're moving past just sophisticated memorization or pattern finding. It demonstrates that with the right approach, and that's key, the strategic pipeline, the careful prompting, these powerful LLMs can tackle incredibly complex, novel problems requiring deep logic. The LLM is like a powerful engine, sure, but how you build the car around it, how you orchestrate its use, that's critical. It's about the system, not just the model in isolation.
Yeah, it really points towards future progress, maybe coming less from just bigger models and more data, and more from designing these clever workflows, these interactive systems, like giving the AI the right tools and processes to think effectively.
Exactly. And the paper even looks ahead, suggesting things like using ensembles of different top models, maybe combine Gemini with Grok or OpenAI's models, or build true multi-agent systems where different AI agents can collaborate, critique each other, combine strengths, leading to even better mathematical results. This really pushes the boundaries for AI in science, in formal verification, potentially even in education. Imagine an AI math tutor that can truly reason through problems with you.
What a deep dive indeed. It's honestly kind of mind-blowing to see AI tackling problems that push the limits of the brightest young human mathematicians. That pipeline design is incredibly clever.
It really makes you think, doesn't it? If AI can now consistently solve problems at the IMO level, what does that mean for other fundamental mathematical challenges? Problems may be considered intractable, needing generations of human thought. Could AI start helping us unlock those? What happens when AI doesn't just solve known problems, but starts contributing genuinely new mathematical insights, theorems we haven't even thought of?
The possibilities are staggering, really. We hope this exploration of Gemini 2.5 Pro at the IMO has sparked some new ideas for you. Until next time, keep digging deeper into this fascinating world of knowledge.